So now I will be shifting to the nonlinear modeling part of this particular session, and I will give you first an overview of one particular nonlinear modeling approach, and then we can have a quick demonstration about application of that particular nonlinear modeling approach. So let me just quickly show you this particular slide to give you a startup in that, and then we can go again to ETAB into SAP 2000 and show you some idea. So the nonlinear models actually can be of three basic types. Let me just open this particular slide, and then I can use this space to explain the basic idea about nonlinear modeling and then have a quick overview of it in SAP 2000. So nonlinear models can be classified into different types, and maybe I'll be highlighting just three of the important types. The first one is the micro models. The micro models will focus on actually uh, the uh, the nonlinearity at a more fundamental level, which means that, for example, if you have a particular reinforced concrete beam like this, you discretize that beam into maybe thousands of small elements along the length and along the cross section, and those elements can be like three-dimensional finite elements, and you can assign nonlinear stress strain relationship, constitutive behaviors, and then you can focus on the nonlinear action at a more fundamental level, at a very micro level. So these are micro models, but obviously they are not very practical for real uh, buildings application, because we have hundreds and thousands of elements, and we may not be uh, model them all nonlinear using this approach, because the models will be really heavy, and they may not provide the results in a short time, which is mostly required in the actual design practice. So the second type is uh, distributed plasticity model. Actually, the second main type should be macro models, and within macro model we have again distributed plasticity. So the first in macro model mean that you focus not at the most fundamental particle level, but you focus on the overall element or cross section or member level. So within that you can have a distributed plasticity models, or you can have what we call as the lumped plasticity models. Lumped plasticity model, the basic idea is that the inelastic action or nonlinear behavior in this second option is actually is distributed along some or whole length of the element. So for example, if you have a beam, the nonlinear action can either be distributed along the full length of the beam, so the full beam will behave in a nonlinear manner, or it can be, in this third option, it can be lumped at certain locations along, for example, the ends of the beam or at the middle of the beam. We can lump the inelastic action at certain points, and within those, between those points, the element can remain elastic. Obviously, this third option, the lumped plasticity models, they will be more practical, and they will be taking less analysis time, because the inelastic action is only modeled at certain points and not along the full length. But distributed plasticity models are relatively more accurate, because uh, they can assign nonlinear behavior uh, at, uh, at along the length actually. It can be full length or part of the length. For example, a beam can be modeled by having a plastic element along a certain length at one corner, and then another plastic element on the other end, and in between them it can be elastic. So it can be elastic, and at two ends it can be inelastic component, and obviously these inelastic components will have a finite length And but in concentrated plasticity or lumped plasticity option, the inelastic action is only available, or it only defined at certain points, so they are kind of zero length inelastic components. So these are sometimes also referred to as plastic hinges. The plastic hinges are the points or components in which the inelastic action of an element is defined, but between two plastic hinges the element is assumed to remain elastic. For distributed option, we can define the inelastic action along a length of an element, and also along full length or part of the length. In case of we apply it for part of a length, obviously we will be having an elastic component in between. So for example, in if you have a particular frame like this and which is subjected to lateral loads, for this particular beam on top, the maximum bending moments and inelastic action you can expect only at the ends. So therefore you should have, if you are using the concentrated or lumped plasticity approach, the second option, you must have two plastic hinges at both ends, which accounts for the nonlinear action at these 2 points, or you should have the distributed plasticity component at both ends, while uh, the part which is in between can remain elastic because it will have lower bending moments, and resultingly the action will remain in the elastic range of response. So I will be actually focusing in this particular demonstration about the distributed plasticity models, and within that I'll be focusing on an approach called fiber modeling approach. Fiber modeling approach. So please keep this overall picture in mind, that you can have micro models or macro models, and within macro models you can again have two approaches depending upon how you actually incorporate the inelastic action in your element or member level. If you incorporate it along the length, it will be distributed, but if you concentrate it at a certain point only, it will become lumped plasticity or concentrated plasticity. In distributed plasticity option, we have an approach called fiber modeling approach, and this I will be explaining in next few minutes, and then I'll show you a demonstration in SAP 2000 about this, how we can have this modeling and how we can see its results and all that. So in order before actually going to um, before actually going to SAP 2000, let me quickly explain its basic concept, what fiber modeling approach is, so that I can show you in SAP after that. Fiber modeling approach. This approach actually incorporates the inelastic action right at the material level. So it because we know that this is the hierarchy. We start with material. The stiffness actually uh, originates from material stiffness, and then cross section stiffness, and then the third level is the member stiffness. And we know that that's how the stiffness is composed of, that it starts with elastic modulus, then it has the cross section property added to that, so it becomes the cross section stiffness, and then the member property is added to that, which is for example the length, and it converts into the element stiffness. So so just like that hierarchy, in nonlinear modeling also we can have we can incorporate inelasticity right at material level, or at cross section level, or at a more you can say macro level, which is the member level. So fiber modeling approach is based on the idea that we can incorporate the nonlinearity right at the material level, so which means we can make this elastic modulus as a variable, and it can vary along vary during the analysis, and therefore the results will become all modified and the behavior will be more realistic. So material nonlinearity is incorporated in fiber modeling approach, And how it is incorporated? We replace this elastic modulus, which we have defined while defining the elastic materials. We replace it with the actual stress strain curve of the material. So here we have to define the actual stress versus strain behavior of the material in SAP 2000 if we want to apply the fiber modeling approach or incorporate the material nonlinearity. So for concrete, we must define a nonlinear stress strain curve. For steel also, we have to define the nonlinear stress strain curve. So we will tell the program that that's how my concrete is going to behave in my model. That's how my steel is going to behave in my model. And then the program can perform nonlinear analysis and tell you a more realistic picture of the structural response. In a nutshell, if I define a nonlinear model in contrast to a linear model, I will say that a nonlinear model is damage aware, which means it can uh, it can tell you the structural damage after the analysis. It will not indefinitely follow the F is equal to KU forever. Instead, it will tell you whether the applied loading has caused a particular damage in the model or whether the structure will be able to sustain that applied loading or not. So in this particular sense, a linear model can be very deceiving because you may be applying a force which is far more than the capacity of your computer model, but the model is not able to predict or capture the failure. While a nonlinear model, on the other hand, will be damage aware, which means it will be able to tell the user after the analysis that this much damage have occurred because of the applied loading and how the structure actually performed under that applied loading. And therefore we know that in the performance based seismic design, nonlinear modeling and nonlinear analysis is at the core of that particular approach. So we have to perform nonlinear dynamic analysis in order to check the performance of a particular design at the hazard levels which are higher than the design level. So coming back to our discussion, the fiber modeling approach, the basic idea is that let's say if we have a element, a beam or a column, or it can be a shear wall also. Let's say this is the, let's say, column like this, and it can also be a shear wall. For example, in the plan view it will look like this. Let's say it is a shear wall leg, so it will be having some reinforcement. Let's say this is a beam and then this is a column which is having some reinforcement. It should obviously be like that, like this. uh, so the basic idea is that we divide that cross section into what we call as material fibers. So let me just draw a column like this, a more clear picture at the bottom like this. So this is a column in three-dimensional view, let's say top of the column. And the basic idea is that I divide this cross section along the both local axes like this, both cross sectional local axes like this. I divide it into what we call as the material fiber. And those fibers can run along the length of that column or a beam or shear wall, any cross section. They can run along the full length of the element or can run along a particular length, for example 10% at both ends or any other particular part of the length, or it can run also along the full length. Now each of that particular fiber, which is for example this one which I am shading now it is running along the whole length. So it is like a you can see that this column is now a bundle of spaghettis which are actually each spaghetti is one fiber, right? And it is running along the length. Each fiber can be associated with a particular material stress strain curve, right? And for example, if there was a reinforcement somewhere here, let's say it has 4 rebars like this. So each of the bar also can be represented by one material fiber, and that particular bar can be assigned with a steel stress strain curve. So you can assume, you can imagine that column is like a bundle of spaghettis, and some of those spaghettis are made of steel, some of them are made of concrete. Or you can say a column is can be assumed like a bundle of some small columns, and each column or fiber is can be having a material of either concrete or steel. So we divide our cross section into what we call as material fibers, which run along the length, and we decide while modeling how much length they should have. And each the basic idea is that each fiber is assigned with a stress strain curve. Similarly, beams also you can do that. Shear walls also you can divide it along the length like this, and each of the fiber, for example this one, can be either made of concrete or steel. Now each fiber has three properties. One is the stress strain curve associated with that fiber. Other is the location of that fiber along the cross section, local along about the local axis. And third is the area of that fiber, the cross sectional area of that fiber. So if I divide this column cross section into 3 by 3 grid, so one concrete fiber will be having the area equal to 1/9 of the total cross sectional area of the column. And if I divide each rebar, I define it as a one steel fiber, then each steel fiber will have an area equal to the cross sectional area of that bar, and their location, which is location, for example this is the 2 and 3 axis of a particular cross section, and if a fiber is located at this particular corner, the location will be actually defined by two coordinates, one about 2 axis, one about 3 axis, and it will be at the center of this particular fiber. So the distance from this origin to the center of this particular fiber, we can have that in 2 coordinate and 3 coordinate. So that particular pair of coordinate numbers will actually be telling you the 2 and 3 distances, actually 3 and 2 distances if we talk about x and y. So therefore the location will be defined like that. And the third thing is the cross sectional area. So material, location and cross sectional area of each fiber will be defined by the user, and then program will actually assign this and then perform the nonlinear analysis. Now you can imagine that when this column will be bending about a particular bending moment, like in this direction, or let's say about this particular direction, some of the fibers will be in axial tension, some will be in axial compression. So the nonlinear action will be captured by the uniaxial stress strain curves of each fiber, which will be either in compression or tension, and all those limit states or important points on this particular curve will be defining the levels of nonlinear action. For example, yield point of the steel, or cracking of concrete or crushing of concrete, for example. And these curves obviously will be in tension and compression both sides. So sigma or stress can be tensile or compressive. And another thing which we have to define while defining the material, with this backbone, which means the stress strain curve, we also have to define the cyclic behavior, or sometimes also called as the hysteretic behavior, which means we have to define in the program how this material will be unloading and reloading when there will be reversal of forces or when there will be cycles of loading. So this particular stress strain curve is actually backbone, but this should also be associated by an hysteretic behavior, hysteretic or cyclic behavior, which will tell the program how it should unload and then reload in the same direction. So the actual material nonlinearity will be captured by both of these properties, backbone plus the cyclic behavior, and then that will be assigned to our fibers, and then fibers can account for the material level nonlinearity at a more fundamental level, at material level, which can be manifested in the cross section level, because when the E is variable, then you have cross sectional stiffness as variable, and ultimately the member stiffness as variable, which means your whole model will be a nonlinear model, and it will be able to tell you what damage it sustained or it exhibited during the analysis. So with this background, let me just at the end quickly go to SAP 2000 and show you how we can implement this fiber modeling approach for one particular element, let's say for reinforced concrete columns, but you can also explore it for other types of elements. So let me now go back to SAP 2000 quickly and show you a quick demonstration about that.